So there's the objectives of this chapter. Identify important questions to determine which PLC device to purchase. Distinguish between Allen Bradley fixed and modular PLCs. We'll look at modular and figure out what's required when we try to select these things. Recognize how to connect sensors and switches to PLC ports or terminals, right? Describe the difference between PLC memory. Describe the method to connect PLC devices to a programming module. So determine, y'all didn't tell me I didn't have a projector.
Oh, we thought we were reading my book.
Which wouldn't be a bad idea, would it? These make pretty good sense. The factors that determine which PLC you would purchase, of course, how much manufacturer support you can get, right? Serviceability, how easy it is for you to fix when it breaks. Flexibility, of course, flexibility gives you the ability to expand, right? Understand that. Expandability, programming software, training, and documentation. More documents they give you. Most PLC manufacturers free to give out their documents on their websites. And one reason they do that is make it available is that if an engineer is out there trying to decide which PLC to purchase, the more information that they have available to them, the more likelihood they're going to buy your hardware. So here in the Allen Bradley line, and this is true on the major manufacturers. They make two types. They make what we call a fixed PLC, and then they make what we call modular PLC. And I think we talked about this last class, right? So what's the advantage of a fixed PLC?
Price.
Yeah, it's price. It's a lot cheaper. And what's the advantage of a modular PLC? Well, you get what you want, right? You can specify and buy what you want. And usually modular PLCs are very expandable. And they're very flexible, right? You understand? So what we have is on a modular PLC, usually we have what we call a rack, also called a chassis. I've heard it called a rack more than I have a chassis. And I think we looked at this last class, right? Had a little look at the 504 up here. So we have a power supply. This is what's converting AC over to DC because the electronics. So we learned on our first lecture that the advantage of DC is that it can be very easy electronically controlled. So your computers and your cell phones and your car radios and all that kind of stuff and your TVs at your house actually operate off DC. But most of the stuff at your house plugs into Alabama Power or TVA, right? And if you live in Bessemer, you're probably on TVA. If you live in anywhere else in Jefferson County, then you're probably on Alabama Power. So we have a power supply. These are the guys that's taking the AC and converting it over to DC for the electronics. Then we have the processor, and then we have different I/O modules and communication modules. I need to add that. So communication allows us to communicate either on a network or between PLCs, right? Now the CPU usually has a communication connector on it that allows us to hook it up to the actual computer. This is the communication portion here. This is using the communication standard called RS-232. Originally, it was specified by the Electronic Industries Association, but EIA disbanded back in 1994, and the standard was taken over by TIA, which is the Telecommunication Industry Standard. So if you look this up, you can look it up under TIA 232, or we're actually in 232C was the last version of this that came out. And that's this guy right here. Now our computers no longer support, so if you had a really, really old computer, you'd see it would have a 9-pin connector on it. So here's RS-232, you know that? So it's what we call a DD9. And it's actually set so it's Murphy proof. You can't plug it in backwards. Used to, if you got a real old computer, you'll probably see a 9-pin connector on the back. This was the main method of transmitting for years. Our computers no longer support it, but our serial interface is what we call USB, right? Universal Serial Bus. So what we have is we have a special dongle that we buy that takes the USB and then converts it over to RS-232. So you'd have to get one of those if you deal with one of these older Allen Bradley PLCs. Just about all your newer PLCs are going to Ethernet. They call Ethernet IP. Of course, I can't communicate with it right now, so I'm trying to figure that out. Okay. Are we okay? Is that okay so far? So we have these come in different sizes for the 504. You can buy it at a 4-slot rack. You can buy it with a 7-slot rack, which is what we got. A 10-slot rack or a 13-slot. We can use extenders or expand it up to a maximum of 30 slots for the 500 series. Okay. So every PLC's got a limit on the number of modules you can hook up to it, because that's the addressing capabilities when it goes out and addresses these modules. Now, the slots are numbered, and what you got to learn in computers, we start numbering from 0. We don't start numbering from 1. So when we look at our modules, now the power supply is not a slot number. CPU would occupy slot 0, so this is slot 0 right here. I've got the door open. This would be 0. That's the CPU for this guy. This would be true for slot 0. Yeah, the CPU. So it's in slot 0, and then this input module is in slot 1, 2. This would be 3, 4, 5, and 6. So when you address a module, you have to specify which slot numbers. So we won't use slot 0. We'll start with slot 1, right? You understand? Because we don't address the CPU, but the CPU's got to address the module.
Slot 1 from the input, slot 2 for output.
Yeah, on this one, I could swap these around if they wasn't all tied down. It's up to you. It's up to you to determine where these slots, what you use in the slot. And you don't even have to use 0 and 1. You could come out here and start at slot 7 and work towards slot 1 if you wanted to. It's just that when they set up this trainer, they decided, which is obvious, to use slot 1 and slot 2 for the 2 I/O modules that they provided with it. But it's actually up to you. You could have a communication module here. So if you wanted to communicate with Ethernet, then you can buy a communication module and not do the RS-232 anymore. It's up to you. That makes sense? So on this one, they decided to put it in slot 1 and slot 2 when they built the trainer. Are we okay? Input output modules can be in any other slot. So the only slot on the modular PLC that is defined is slot 0. And what's got to go in slot 0? The CPU. These are not 6500s. So fixed PLC, so this is a little different in that the fixed PLC does not have slots. the CPU, the I/O, and everything is built into the unit, right? And we passed around the 1000 last class. It's a fixed PLC. So it has no slots, but we still address by slot number. Does that make sense? So on the fixed PLC, like the MicroLogic 1000, your I/O will be in slot 0. We consider slot 0, but it's a logical slot number. It's not a physical slot number because they don't have slots, right? You understand this? So on a modular PLC, on this one, if I wanted to address the input ports, I would have to tell it slot 1. On the fixed PLC, if I wanted to address the slot, the input output, I would use slot 0 because the CPU does not occupy a slot. So that kind of gets people confused sometimes. Does it confuse you? No. Because it has those slots, right? You understand that? Yeah, but you still address you address the I/O like they are in a slot, even on a fixed PLC. So I/O ports and voltage and current rating cannot be altered, right, on a fixed PLC. However, a 2-slot chassis can be added, so more I/O modules can be installed. Most of your newer fixed PLCs, I refer to them as a hybrid, and I'll try to show y'all that, where you can add modules to them. But usually slot 0 is already taken by the internal slot. Power supply supplies power to the chassis, backplane, and thus the processor, modules, and peripherals attached to the chassis. Peripheral, what's a peripheral? Outside the computer, right? But you're not going to hear this term much out in the field. Most people out in the field call these field devices. And that's just the terminology of the trade. People in computers will call them peripherals, but most people out in PLC refers to these as field devices. So these are actually what we're connecting to the input and the output ports of the PLC. Are we okay? So these PLCs, this is a SLC 500 modules, and these are all these are different processors, and this is not really important to know. We've got a 504. I need to go back and look at it. Now, usually what they do on the side of the CPU, on the side of the fixed PLC, what they do is they have a label on it, and then this is where most of the information about your CPU is. So this is the SLC 500. Oh, no, we can't see it. So on modular PLCs, they usually put it on the door for the module. Oh yeah, here it is. Here's it right here. I'm going to see it on the bottom. So this is a 1747 L541. And then we can look up in the chart, and this will be available in right here. L47, L5. Did I say 41 or 51? 41. Yeah, right here. So this has got 16K of memory in it, which don't seem like much, but this guy don't do graphics, and we talked about that. That's primarily what all the memory in your computer is in there for, is to handle multitasking, which means we can have more than one application inside our memory at the same time, and also graphics. Graphics is what he's simply telling me. These guys don't do graphics in one program at a time. So our modules fall into two categories. Your book uses the term discrete and variable, but out in the field they call them digital, and they call them digital, or they call them binary. The book refers to these as discrete. Oops, I didn't do that. What does digital mean?
0, 1.
0, 1s, true, falses. We'll use those terms a lot. These means your sensors are you put a push button. It's either what?
On or off.
It's either on or off, right? And most of your sensors, when they censor what they're looking for, is either on or off. So primarily, just about all of, I'm not going to say that, most of the input devices that we hook up to the input ports are digital. But then, of course, we got to understand that we live in an analog world. So digital is either true or false, right? And analog. This gives us the ability to represent basically an infinite number of combinations varying between two things. So temperature, we live in an analog world, right? You understand? As far as the physical world is analog. Temperature does not vary. It's like the high today is supposed to be about like 89 and the low was supposed to be 75. If it was digital, it would go from 75 to 89 with no variations at all. That would be digital. But it don't do that, right? You understand? Light, our days are analog, right? You understand? So analog modules, these are going to have to, what they do, and I don't know if this is in the textbook or not, but inside the PLC on an analog module, depending on which way you're going, so inside the module itself, if it's an input module, inside the actual module itself would have an analog to digital converter. This is input. I need to put input. Because the computer's digital, right? You understand? And we're bringing in an analog input. Somewhere out of space. It's called an ADC. And the output would have a digital analog converter. And this is on the module. Or a DAC. ADC, and then we might have networking modules that gives us the ability to do what? Network the PLCs together and eventually take us back to a computer somewhere. We okay?
What about that
Specialty. Yeah. So these would just be specialty IO modules. So normally the primary method we use, we got three quantities if we're going to send signals electrically, we can't do it with this. In my computer, can't do it. We can't send resistance, right? So what's the other two things we have? We can send voltage, or we can send current. Now the predominant method of sending information is voltage. So we'd say, okay, one voltage, if it's digital, one voltage would equal to a 1, and so it's usually, and then the next voltage would equal to a 0, right? Understand that? When we send current, then the primary way we do that in industry is we use what they call a current loop, and it's usually 20 to 40 milliamps. Now, why we do that is that if we use voltage, these are going to be low current or high resistance circuits, which makes them more noisy to electromagnetic interference. It's almost impossible for electromagnetic interference to produce a current. So we go to a low resistance circuit and we use a current where 4 milliamps equals 0 and 20 milliamps would be equal to 1. Or if I was sending analog, 4 milliamps would be minimum and 20 milliamps would be maximum. And you'll run into that a lot in industry because it's almost impervious to electromagnetic interference. And when you get out in industry, there's a lot of electromagnetic interference out there, right? But voltage is easier to work with. Current always consumes power. Voltage only produces power when the voltage is available. When the voltage is setting at 0, there's no power being consumed at all. So if I've got a PLC that outputs voltage, and I need to do a current loop, then I would have to buy a module that supports current loop, right? Understand that? An input current loop or an output current loop. So specialty modules get things that we don't normally understand. So we could go back or we could look up the 500 and look up series and look at what modules are available with this PLC. And you see it's got all types of modules, just besides what? Digital input and digital output. Now these modules we have up here, these are digital. And the PLCs, I'll hook up one of the 1100s. This guy down here, and let y'all see basically analog. It's got analog inputs on it. Each input and output module has several ports or terminals. For example, input modules, one may be 16, output module may be 8, so they don't have to be the same. The 504 that we have up here, it has a 16 inputs and 16 outputs on both the modules. We got one input module and one output, but they don't have to be. It's up to you on a module PLC. It's up to you to decide how many inputs you want and how many outputs you want. Of course, the more inputs that you have, the more expensive the module will be, right? And depending on what you got. Allen Bradley, and we'll talk about that. So module numbers is kind of misleading, but we'll look at that when we get there. Specifies when they are specifically used in ladder diagrams. Now we talked about ladder, right? Okay. Okay. And this is still the primary method of programming a PLC. So what we have is we have input ports, and these are single bit, and then we're going to have a terminal on the input module. So these are usually either Phillips, most of them are straight slot. And then what we're going to hook up to this, we would come up here and we would run a wire to it, right? Understand. And then of course, and we'll talk about this in a minute, and then my push button might be right here, or whatever I'm using. Now it depends on what this thing is looking for. So right now we'll come up here and I'll just connect this up to like plus 24 volts. So now if it's pressed, then I would get 24 volts in, right? Understand, to that input. If I let it go, I get 0. Now notice this has got, it's got an I there. Can y'all see it right there? Which, what do you think that stands for? And then beside it, it's got a number. So it's got 0. And that's not an O, that's 0. You notice they go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this guy here would have 12 inputs. Because it starts with what? 0. This would be my output. So notice, and this gets us, and somebody in this class is going to do that. They're going to use a 0 instead of an O, or vice versa. So when Siemens came out, they changed the designator for output to Q. Somebody in that class, somebody in here is going to do what? they're going to put a 0 instead of an O or an O instead of a 0. So over here you see this is an O, and O stands for what? Output, you know. And then 0 through 1. So this would be this module would have 8 ports or 8 terminals on it. Make sense? And so we'd say O and then 0. We're going to do this a little, how we address them in our program is a little different. We'll look at that. So input devices are going to connect to the input port, and output devices are connected to the output port. And so I might take a screw right here, and I might hook this up to a light bulb. Then over here, I might have a common or ground. Okay. And somehow we're going to output, and it's going to either turn the light on or turn the light off, but this is any output device. So these guys are not rated for a lot of current. So normally if we're going to drive something that needs a lot of current, we'll run it through a relay. But the PLC will put out enough current to pull in a relay, and then the relay, we can either control DC or AC with the relay. So this is an example. So what we've got here is, this is 120 volts. And it don't tell if it's AC or D. Yeah, it does, because it's got a plus. And then what we do is we bring this out, and then all our inputs are connected to this. Huh? No, it means DC. If it was AC, it wouldn't have a sign. So AC has no sign, right? You understand? Because why? Because it changes all the time, right? Like I said, on ours, it's only positive for 60 cycles. It's only positive for 8.333 milliseconds. So basically, it has no sign. So this is why when you measure AC with your meter, it don't make any difference where you put the black lead and where you put the red lead. It's going to measure the same, because there's technically no negative polarity. So here we're hooking up push buttons. These could also be sensors. And then over here, notice they're outputting this. So this has to be the minus, and this has to be the plus, just on this arrangement, for if it's a DC power supply. But it don't. It all depends on the PLC. And notice all these devices are common over here. Then we would output. This would be a light. This would be 2 lights and some motors and a bell. Makes sense? Are you okay? Typical rated for low voltage, low current, ordinarily connected to IO devices. And this is not true, guys. It all depends. American wire gauge number 14. Even NEC rates this thing at 15 amps. And there's no way in the world we're going to get 15 amps out of a PLC, unless it's got what we call relay output. Normally, a normal rule of thumb, and this is something you have to look out for, is your output modules are usually rated around 2 amps. If you don't know it, the thing you need to do is what? Look it up, right? So don't take for granted how much an input module will draw. Usually the input module draws very low current. The output, this is where your loads are connected to. Like I said, a rule of thumb is if you don't know, if you can't get the documentation, it's a maximum of 2 amps. But that's not true. You need to look it up, right? Understand that. And all this information is available on the manufacturer's website. Most of the time you can just load it up. You can look up the module number or the model number of the PLC. You can type that in, and it'll bring you up the specifications, and it'll tell you exactly what the inputs need and what the outputs can provide. I don't think I've ever seen one using 14 gauge wire.
Pretty big.
Yeah, it is. That's what all your That's the main wiring on your house. We use two main wiring on our house for, we use either 14 gauge or 12 gauge. That 14 gauge is rated at, NEC rates 14 gauge at 15 amps, and they rate 12 gauge at 20 amps. And that would be for your base plugs. After that, when we get out to air conditioning and stuff like that, you know, the wire size has to go up. So usually you're going to see probably a maximum of, I don't know, maybe, I don't know. I was going to say 24, but 24 is little. But you need to use a wire gauge that's going to support what you're driving, right? For most applications, the output devices require large voltage. That's not necessarily true. This is in the book. Normally, Morgan, originally, and this book was written a long time ago, originally a lot of the drive, what advantage does a high voltage have over low voltage? The voltage doesn't determine the power. The voltage determines what determines the power needed in a circuit. What load we have connected to that, right? Understand that. Now your power supply has the ability to have the ability to put out the required power, right, at a certain voltage. So P is equal to, our primary formula is P is equal to what? I times V. So I is equal to P over V. So that means the higher I can make the voltage, the higher the voltage the device is rated at. Now you just can't go out and do it yourself. So every load that we have is specified a voltage. Now a resistor that you ran into DC, the voltage is not specified. But just about every load in your house has a power rating, even a light bulb. You go out and buy a light bulb, one of the things they give you is what? The watts. Now, the higher the voltage that device is rated at, the less current's required to provide that what? Power. Which means what? We don't get more power out of 1,000 volts, and we could get the same amount of power out of 100 if it's rated for it. Out of 100 volts, that we could get the same amount of power out of 5 volts. Look at your car battery out there, right? Your car battery probably provides, most of them is rated like 200 amps at 12 volts. That's 1,200 watts of power that little old car battery can. It's not lead, it's big. Car battery can put out. But if you get into an electric car, they're not going to use 12 volts. They're going to use like 660 volts. Why? They can get more power with smaller gauge wire. Look at the wires on your car battery. How big are them suckers? Yeah, they're big size wires, right? You understand if it was 660 volts, you could run a starter, right? 660 volts with 2 amps, you could get 1,200 watts out of that. And now you can use a wire that's rated at 2 amps instead of a wire that's rated at 100 amps, right? You understand that? So the only advantage of higher voltage is that you can use smaller gauge wire and smaller components. Your relays don't have to be as big. The little tiny small relays, right? You understand that? Because what determines the amount of power in a circuit? The load. And then the load is going to be rated around the voltage. All your high wattage loads at your house run off of what? 240. Right? Because why? Because now we can run smaller gauge what? Wire. And the relays inside the run your compressor can be smaller size relays. Because it doesn't require to control that much current, right? You understand that?
So more voltage, less wire.
Smaller gauge. Well, it depends on the load, right? So what's wired, what's conductors rated at? What do we rate conductors at? Just conductors. They're rated in one thing. No, that's not true. They're rated in two things. They're rated in current and ohms per 1,000 feet. That's the two things they're rated in. What's resistors rated? What's the two things resistors rated? Well, three. What's the three things resistors are rated in?
Size.
Anybody size?
Oh, the size of
Now, the ohm value. When you say size, you got to be careful because you're talking about. I could have a real big resistor that's rated at 1 ohm, right? So the ohm value, right, or the resistance. What else is? What are they rated? Wattage. How much wattage they can dissipate before they burn up, right? And what's the third thing? Well, that would be wattage. It's rated in tolerance, right? So if an output device requires a larger voltage and a larger current, then what we'll do is the PLC will pick up a relay. And the relay will provide the watt, the larger voltage and larger current. A magnetic relay should be used to connect larger voltage and current equipment to the output device. PLC output ports provide voltage and current to the input coils of the magnetic relay, and the relay picks up the device, right? So we're not doing away with relays. So we'll still have relays in PLCs. You'll see a lot of them. It's just going to be a lot less of them. Syncing and sourcing. So this is pretty important to understand. The book just touches on this. Now, syncing and sourcing only applies to DC. AC has no polarity because the polarity keeps doing what? Changing. But when we come up here and we hook up loads, so what I'm going to do, this is L1, and this is where your input devices are going to connect to. And then your output devices are going to connect to L2. Or some semblance of that. I'm just using lights right now. Now, if this is DC, which is going to be plus and which is going to be minus? Don't make any difference. Current's current. Light bulbs don't care if it, relays don't care if it flows from left to right or right to left. They don't care. Okay. So if I come over here and put the plus right there, and I put the minus over here, which most people want to do that, then notice this is the common right here. So a common is just where you connect everything to, right? You understand that? So notice my push buttons are using the plus for the common, right? You understand? And my light bulbs are using the minus of the common. But I could have just as well made this minus and made this plus. And now my push buttons are using the minus for the common, and my outputs are using the plus for the common. You understand? So this came up through DC. Through digital. And we really don't need to understand how digital circuits work. But if the minus is used as the common in PLCs, this is referred to as syncing. And if the plus is used as the common, this is referred to as sourcing.
So, like sources like power and things like that.
No, it's just the common. Current has to flow through the load to produce work. And basically, there's no advantage to syncing or sourcing on DC. It's just that different companies do it different ways. And normally if a company does it the same way, that every PLC that they buy is going to do it the same way, so the technicians does not get what? Confused. Yeah, I was thinking of the NPN sensor, but you don't need to know that in this class. So sensors are rated as either solid state sensors are rated as either NPN or PNP. An NPN is a sinking sensor and a PNP is a sourcing sensor. So when I come up here and look at these these modules on this PLC, let me bring my camera back up. I didn't do that. And I look at this input module right here. Oops. On my left. On my Can y'all see? You don't see that? It says it's what? See it? See? This one says what? So it means this input module provides the minus, and the output provides the plus. So what we would have to do on a sinking module second crisis. So let's say this is input 0, and it's what? Yeah, it's what? Sinking. Let me redraw this a little bit. I forgot one major thing. I had to put an input device over here. So this guy's sinking. What has to be over here? It's got to be, yeah, that's good. Because we have a current. So this guy provides the return. That's what sinking means. It provides the minus, so we have to have plus. So that means if I got a sinking input module, then all my input devices have to be wired as sourcing. Now my output devices are sourcing, so they are providing the plus. And then let me, wait a second, y'all draw. I forgot something over here too. That right there would burn us up. So over here we'll have our load. So if this provides the plus, then what's this got to be over here? That's got to be the minus. And then this would be another port, so this might be input 1, and this might be output 2. It don't make any difference. And this might be output 1. You don't have to. And then this provides the plus. Then so if we got sourcing outputs, then that means all your devices that you connect to have to be syncing devices. Now relays don't care and lights don't care, which is basically all we're using here.
I wrote it. I wrote it. The minus is used.
It is. You got a syncing module. So the module itself is syncing. That's correct. If the module is syncing, then the input devices have to provide the what? They have the source. Because we got to have current flow, right? So these guys, that's a syncing output. So that means on all my input devices, I will use a positive common. And this is the predominant way we do it over here in the United States. Is we use syncing input modules and sourcing output modules. But I'm not going to say you're not going to run into it, right? And this would be a problem because you're the one that's wiring that thing up. And so if you go a minus to a minus, it's not going to hurt anything. It's just that your inputs won't work anymore. You'll get truths all the time, right? You understand that? Or if you take a sourcing and hook it up to sourcing, then nothing will work because you got plus on both sides.
Like put a barrier on the wrong side.
Or connecting both your lights to the positive terminal, right?
But these systems basically all input.
The input devices are plus. The ports themselves are syncing for these PLCs. And this is true and this is not true for some PLCs. Some PLC give you the ability to set up whether you want to be syncing or sourcing. So like this Allen Bradley 1200 PLC, if I can mess up here. Got it. Trying to bring up my. Applies to DC. AC, we don't worry about it.
The camera makes you look old.
You, not me, right? It's selective. It's a selective camera. So this is what we're going to do, and we're going to modify this a little bit. So what we have on our PLC. You're going to have one terminal that's going to be rated common. Common means it's just a common connection. Now, normally we think of it as the return, but that's not exactly always true. So, and that's the problem we have because normally when we draw circuits, we have one of our leads being the common. But what does common mean? Well, it's just a common connection point for the devices. And problem in DC, we think about our cars and stuff like that, and your car runs a minus common. So a lot of people think that common's got to be minus all the time, but that's not true. In fact, we can share common between power supplies. So this could be a plus, and this is the way your trainer does, by the way. And then we can share a common, and it'll come back to its source. So this is the way the trainer is laid out. So if you ever look at the trainer, you got a plus DC, and then you got a common, which they refer to as ground. So even the trainer uses that term incorrectly. So on that trainer, you could take your ohm meter and go between what the trainer calls ground and you can measure it to that little round terminal on your power plug, and it's going to measure infinity. So the trainer does not run a true ground; it runs what they call a common. So even in the trade, they misuse those terms. So normally, what ground should mean is that somewhere the system is referenced to earth ground. And this right here would be labeled minus. So this is, and so if I put my load between here, then this would be plus, this would be minus in relative to that, but if over here, this right here would be, I got them back. Yeah. So this would be plus in reference to that. This is your trainer. This is your trainer. So we could switch between those two power supplies, and I could generate AC, right? Which is what this function generator up here does. So it comes in, it brings in Alabama Power, TVA, 120 volts, runs it through a transformer, steps it down to make it safe, runs it through, generates a plus and minus DC power supply, and now we can electronically regenerate what? AC. But now I control the amplitude and I can control the frequency. Just like your car radio. Your car radio, speakers will burn up if you put DC on them. So what does your car radio do? It takes that 12 volt battery, somehow it generates a plus and minus DC out of that thing, and that's what goes to your speaker. The same situation right here. So notice here, the plus is here on the power supply, the minus is here. Okay. So that means this module, this is input, this would be sourcing, and the devices themselves would have to be what? So when a push button don't care, but electronics will care. So if you have what we call a solid state sensor, an electronic sensor, then by George, it's either going to be a syncing sensor and it's going to be a sourcing sensor. Right? You understand? And if you take a syncing sensor and hook it up to a syncing input, then it's not going to do anything, right? Or if you take a sourcing sensor and hook it up to a sourcing input. So if your inputs are sourcing, then your sensor, you got to buy what? Syncing sensors. And odds are the company makes them in both versions, right? You understand? So here you got something that's broke, and you buy the first one you see, and you buy the wrong one. Pay $200 for the dang thing, and then it comes in and it don't work. And then odds are well, probably not if you tore it out of the package and hooked it up to something. Or now you blame the PLC. You say, well, it must be the PLC's bad. Then you replace your PLC, right? You understand? Then you do what? You hook up the sensor and it's still bad. So here we're using a minus common. So that means my input module is syncing. So my output, my actual devices are going to have to be what? So that makes sense now. Everybody okay? So usually the memory in the PLC, let's take a 2-minute break. So the two categories of memory is what we call user memory. This is where you're going to put your programs in, right, when you upload them, when you download them to the PLC. And then system memory, this is the memory that's used by the processor itself. This will hold the operating system that is basically transparent to you inside the PLC, right? And you can look at some of this output status, input status, output status, timer. So timers and counters as far as we're going to get to in this class. If you want to get into the math and the sequencers and the high level things that we can't do with everything that we're doing here can be done with relays or relay logic, or you can buy modules. Then in advanced PLC, we get into the things that the computer portion of the PLC allows us to do math, it allows us to do logic, it allows us to set up what we call sequencers. We can do compares and all kinds of stuff. That would be what we call advanced PLCs, or we call PLC2. So your memory inside MicroLogic, or we're using the RS Logix 500. That's the program and application we're going to be using. And then what they do is they divide the memory up. They divide the memory up into these categories. What we've done on new PLCs is they let the user decide how to arrange the memory. The RS Logix 500 originally set up this memory for you. So on the RS Logix 5000, you set up where you want your timers to be, your counters to be, your inputs and your outputs. And also on the Siemens PLC, the Step 7 does that. But ours will be divided up. Ours will be divided up for us. Are we okay? Make sense? So this is showing that. So this is RS Logix 500. Oops. This is what we're doing, and we'll look at this. So first thing is that usually the application has the ability to program a lot of different PLCs. And the machine language that they talk might not be the same for every PLC. So when you open up a new project or a new program, first thing you're going to have to do is specify what PLC or what CPU you're programming for. So as soon as I say new, notice it does what? Give you a listing of all the PLCs or all the CPUs that this application supports. And where would you find this information at? Well, what you do is you look on the side of the PLC or the CPU, or on a modular PLC, you'd open up the door and you'd look and see what module, what part number that is. And you select it by part numbers. I'm going to do the MicroLogic 1100 video. Now what we have over here, this is what we call the project tree. And here's your memory right here. Data files, they call them data files. So this file this is dedicated to what? Output. This is dedicated to what? Input. This is dedicated to status. This is dedicated to what we call binary bits, and we'll look at that as we go on. This is dedicated to what? Timers. This is dedicated to counters. This is control registers. Integers. What's an integer? That's a whole number, right? So that's numbers without fractions. And then the other type of numbers we have is what we call floating point numbers. Floating point numbers, these are fractional numbers. These allows these numbers to have fractions. Are we okay? So right now this is dedicated. This is dedicated to these devices. Are we okay? And like I said, on your new PLCs, you decide how to dedicate your memory. On your older PLCs, RS Logix 500, this is set up for you. Some of your newer PLCs, even though they run on so the MicroLogic 1100, you can add to this. It's got more memory in it. I think this 1100 has like 100K of memory in it. So what that means, it's got some extra memory in there. So you can, if you need more counters, you can specify more counters. And we'll look at that because these are limited because the memory is identified, right? We'll talk about that as we go. Oh, that's another thing I need to show you. The first, this memory right here though, where's it at, Rich? S0 and S1, these are system memories. You can't do anything with those. Some PLCs now don't even put it up there because they're just there. We can't do anything about it anymore. So that's where your operating system's at, everything that's needed by the processor to run, control the PLC. And then we have something called ladder 2. This is your actual program. So down here, see file 2. This is ladder 2. So this is where I would come in, and this would be where I actually come in and build a program. Okay. So on this one, that would be your ladder logic program. Then you have the dedicated memory that's sitting up here, right? Everybody okay? Peripherals. Here they're talking about other PCs, other printers. Of course, peripherals. We say these are things that we connect to the computer, right? You understand? And what does most people in the PLC call these? They don't call them peripherals. They call them field devices. And then programming devices. And we've got we call them 504s, but actually they're technical. It's 5/04. So it's actually PLC 5 revision 04. But most people, when they talk about these, they just call them 504s or 502s, and they don't put the slash in. This tells you the communication channel. So DH 485. That's a standard for the way we communicate. So we could look up these. So you could go up on the internet and you could look up DH 485. So the book doesn't give you much information about these, but these are just communication standards. So these are basically what we would do to connect to the PLC. So we got to be able to connect our computer to the PLC. And then of course, what we'd also like to do is we'd like to have the ability to connect in bigger applications. We would like these PLCs to be able to share information, right? Understand? So 485, DH485, it's got certain voltage levels it uses. It's got certain current levels that's available. All you probably need to know is that if you got DH485, then it's got to be supported by all your devices, right? If it's not supported by all your devices, then you might have to buy a module for a modular PLC that supports that. If you got a fixed PLC, then you got to know that if it uses Ethernet and all your other devices uses 485, then you're going to have some type of converter that goes between Ethernet and 485. So you can't take a 485 and connect it to an Ethernet jack, right? That makes sense? But you can buy adapters that adapt between these two. More and more, guys, we're going to, more and more your newer PLCs are going to Ethernet. And why? Because it's all over the place. So instead of me having special equipment and all this other kind of stuff, if you've got Ethernet, then your switches and your routers you could buy them at Walmart. Odds are you wouldn't, because they wouldn't be industry grade. But all this technology is already out there, right? You understand? And if all my PLCs use the same inputs, then so this is the 1100. This is one of the first ones that they went to. This is most of y'all use a Wi-Fi version of Ethernet. Usually when we talk about Ethernet, we're talking about the hardwired version of it. So this is Ethernet right here. This uses a connector we call an RJ45. It looks kind of like, have you ever seen an Ethernet cable? I think I might have one right here. And what's nice is that you're not a laptop. Just about all of your not a tablet. Just about all your laptops support this guy right here. Okay. If you take the PLC 3 class, which is PLCs and automated systems, we let you build one of those cables. This is a different variation of the ORS-232 interface. It uses a lot smaller connector because the RS-232 uses that big 9-pin connector. This is what personal computers started going to, and so this is a pretty standard. So this is that RS-232 connection right here. But what's nice about that, we can either use either way on this PLC. Just about all your PLCs now, this is what you get. So all your next version of Allen Bradley's use, we call them compact logics. These are called micro logics. The compact logics use Ethernet, what they call Ethernet IP. Siemens calls it Profinet. So if you're out in the Siemens industry, if you hear the term Profinet, Allen Bradley calls it Ethernet IP, and then Siemens calls it Profinet. They're the same thing, uses RJ45. Usually it's a lot stronger cable than what I pass out here. And this is what we call UTP cable, which stands for unshielded twisted pair. It's a lot cheaper. When you get out in the industry, it's probably going to be what they call shielded twisted pair. So what they do, they add a metal shield around the cable to help eliminate some of the electromagnetic interference. And it'll be green, by the way. So if you ever get out there and you see these green cables going from PLC to PLC, then that's Profinet. If it's purple, it's going to be Profibus. So when you connect to it, your PLC is going to have a method that you connect your primary. Originally, when we got into PLCs, like I said, you had an external. Your computer was your CPU did everything. It had the application in it. It had everything. So what we did is we'd hook up dumb terminals to these things. And then the dumb terminals would have all the push buttons and stuff, or inputs and outputs, and that's the way you wrote your program. Now what they're doing is your PLCs have very little memory in it, and then we program them with some type of external device like a personal computer, which is probably the predominant way of doing it. So now your PLC don't have all those, the operating systems now are very small, everything's binary, so we get by with a lot less memory inside the PLC. Oops. So some of the methods, Allen Bradley PLCs is the DH485, which is basically just a variation of RS-232. DH is data highway. This guy's kind of weird in that it doesn't use a connection. It's actually hardwired. So we run a so this is This is the RS-232 connector, and then that's your DN connector, and then this is the DH right here. So that literally, you bring the wires in, and it's got 3 terminals. It's a 3-wire cable, but it's going to be shielded. Y'all understand what shielded is? It means it's got a metal braid around the outside to help them. And this would be for the data highway right here. So this guy supports basically 3 different. These 2 are the same. It's just a different connector that you use. And like I said, if you want more information on them, you look them up. But basically, all we're saying in this class is that whatever's available to the PLC, then that's what you've got to use, right? You understand? If you don't use the same communication standard, then you're going to have to go through some type of adapter or some type of converter to convert it over. It's just like my computer doesn't support any of these. Well, I'm sorry, it supports Ethernet IP because it's got the network connector on the side, but it doesn't support the DH485. So what do I have? Yeah, I got this converter right here. That's it right there. Right. It takes me from standard USB over to this DH485 or the RS-232 connector. Make sense?
So I have to hook my iPhone to this?
If you have got a USB slot, you could hook it up. If you got it on your iPhone, you have USB on your iPhone. Okay. You could hook it up, but it won't do you any good unless you can. But you have to have the application. Yeah. So yeah, we could hook it up. I mean, but it wouldn't hurt anything, but you wouldn't do it unless you had the application. And your application, I'm sure you can't find this RS Logic 500 for your iPhone. Because your application what is an application program? Well, an application program utilizes the operating system. So this is why I cannot download a game that's written for the Android phone into my phone, because even though the game appears to be the same, it goes to a different translation, right? Because the operating systems are different. So let's look for it. So yeah, you could hook it up. It wouldn't. Huh?
I can't do
Only, I think, yeah, okay. My youngest. Oh, what's a modem? What's a modem? What we have to do is so multiplexing is what is media? What is media? It's what information goes through. So what medium am I using right now? Air, right? So I'm using air. So, and how many different devices do we have in the air right now, communicating in the air right now? A lot. So we got to have the ability to have multiple devices out there, and they're all on at the same time, and we refer to that as multiplexing. So multiplexing allows different multiple devices to share the same media. We have what we call baseband. Everybody heard of baseband? Ethernet is baseband. Baseband means we have one device on the media at any one time. So one device at one time. And what they do is they divide the data up into what we call packets. So the way Ethernet works is that listens, if there's nobody out there, it puts a packet off, it puts a packet on the media, then it comes off and lets somebody else does. This is Wi-Fi, guys. Baseband means you have multiple devices on the media at the same time. To do that, they have to do something called modulation. They take the information and place it on what we call a carrier. And then each one of you has your own carrier. So multiple devices share the bandwidth at the same time. The act of taking information and putting it on a carrier is called modulation. The act of taking it off the media and splitting it back out is called demodulation. Hence the term modem, which is short for what? Modulator or demodulator. So modulation allows you to have baseband, allows you to have broadband. So broadband is when we have multiple, that's the term we use in networking. That's when you have multiple devices on the media at the same time. So now you'll know what modem is. It's what? Modulator, demodulator. So it takes your information, places it on a carrier. Your carrier on your cable, if you got cable at the house, it's sharing it not only with that. How many cables do you have coming into your house? Cables. One. How many things on that cable at the same time? Yeah, because everything's modulated, right? So what you're doing when you tune in a station is you're telling it what carrier to demodulate. And it blocks everybody else. So that's called base. So baseband is one device at any one time. Broadband is modulation. And you share the bandwidth on that.
Spell, is that B-A-N or B-A-N?
What's that? Everybody's heard of that.
Baseband.
So we call it baseband, B-A-N-D.
Oh, baseband.
And everybody's heard of broadband. Because you deal with the internet, right? Yeah, everybody's heard of broadband, but you didn't know what that meant, did you? So that's one of the terms y'all been using. That's one of the terms y'all probably been using a lot, but you have no idea what broadband is.
I know I got lousy service.
So you got very poor bandwidth. So bandwidth is on internet, that's the range of frequencies your internet service provider assigns you. And you can't be above the total bandwidth of the media that you're sending information through. Let's modem. Now we can send the information in two directions. We can use what we call full duplex. Full duplex means we send it two directions at the same time. So your phones are full duplex. I don't know if you ever communicated like on CD or ham radio or stuff like that. That's half duplex. This is two directions, not at the same time. Well, depends on the two-way radios. Most two-way radios are half duplex. You got to key them up and you talk a little bit, and then when you get through, you say over, and then the other person knows it's time for them to pick up. That is half duplex. Your cell phone is full duplex. What can you do on your cell phone? You can talk and listen at the same time. Sometimes you have to tell your partner, shh, let me talk. CB is half duplex. Ham radio is half duplex. Most of the communication, a lot of places when you go, a lot of people buy these little radios when you go to the beach so you can communicate with your kids, right? Yeah, little walkie-talkies, those are half duplex. Ethernet is half duplex. One device on the media at any one time. It could be going left to right. It could be going from the transmitter to the receiver or from the receiver to the transmitter. So these are half duplex. That's something, so different types of communication has different, and we have what we call simplex. What do you think simplex is? Simplex is one direction. So broadcast radio, so your radio in your car is simplex, right? You understand? One direction from the what? From the transmitter to the receiver. Your receiver can't send information back. That's called simplex. We don't run into that. Full duplex allows two-way communication between two devices, but they need to say at the same time. Half duplex means we allow it in one direction at a time. And this is depending on the PLC. But we'll have to look and see how many devices we can actually hook up. So every communication standard is going to specify the number of devices you can hook up. I think for USB it's like 128 on a single host port. ASCII. I know what ASCII stands for.
Throughout communication.
Close. It is. That's what it does. There you go. There you go. Are you reading that from somewhere? American Standard Code for Information Interchange. And then we use what we call an acronym. An acronym is you come up here and you take the first letter off each pertinent word, so they don't consider 4 to be pertinent. And then you use that to create another word. So we call this ASCII. Some people call it ASCII too, but that's incorrect.
Oh, so what's called ASCII?
Some people call it ASCII 2. They interpret the II out there as the Roman numeral 2.
Yeah.
But it's no such thing as ASCII 2. It's ASCII. And all this is we realize that the computer only deals with ones and zeros. Right? You understand? But so that means if I was going to communicate with this guy in its language, the only thing on my computer keyboard I would have would be ones and zeros. But when I look at my keyboard, I have all these letters on there. So what happens when I press the letter A, it does not send an A, it sends a code that represents what? A. And that's what the ASCII code is. That's these codes. Now these don't use ASCII, these use a special code that was designed around IBM. They call it a key scan code, but you understand that. PLCs, if they want to display text on something, then odds are they're going to use what we call the ASCII code. This was under my pillow, so Mr. Raymond was sitting on that. Everybody gets one. We're looking at the back. So one of the commands we're going to have with our PLC is we're going to be able to not only send information, we're going to have to send text, right? You understand that? And the primary method used is ASCII, even around the world. In fact, when they came out with the internet, the code we used to send text was ASCII code. So that means nobody in the world, if you were going to set up a web page and you were going to put information on that, you had to do it in ASCII. And this is the Latin alphabet. But after a while, they adopted another code called Unicode. I don't know if y'all have heard of Unicode or not, but Unicode is what we use on the internet now. But the lower 8 bits is still the ASCII code. So that's ASCII code on the back, and you can see, so an uppercase C. Now the way you read it, and we're going to talk about this later, is the way you read it is you read the column number first, and then you read what row it's in. So an uppercase C, what would the code be? Yeah, 43.
That's capital C.
That's a capital C. Lowercase would be over in 60s, right? So this would be the binary code. You see how fast I went through that? That would be the binary code right there. So what they're doing, they're giving it to in another base that we'll talk about in the next chapter. So what would I send if I was going to send my name? I was going to do Rich, lowercase I, C, H. So what would be the ASCII code for an R? What would be the ASCII code for a lowercase I? 6 what? 69. What would be the ASCII code for a lowercase c? 63. And what would be the ASCII code for an lowercase h? I'm sorry. Lowercase h. 68. H? 68. No, this is binary. We're going to talk about that in the next chapter. But notice, if they put the binary codes out there, it'd be very complicated. If they put the way you gave them to me, I was able to go to the binary without even thinking about it. This is that base, the number system you're looking at, that chart is something called hexadecimal. We'll look at that next chapter. But I send these codes. So when I come over and hit this A key on my computer, if I hit the shift key, it sends one code, right? You understand? If I don't hit the shift key, it sends another code. This comes into the CPU as a binary code, and then your application processes it to mean what it wants to be. We call this a soft keyboard. So the A can mean, this key that's got the A on top of it can mean several different things. It depends on the application. If you ever played games on your computer, you know, they make those keys mean anything they want to, right? Because all it gets is a code. It gets a binary code back from the key, and then your application determines what that means. Now, what they decided to do, so over here, oops, dang it. These are old, no. So here, I'm going to insert a symbol. And down here, it's got, can y'all see what this says? Unicode. And they're giving me to them in hex. But it's still, this is Unicode. This is what's used by the internet, and also this is used by most of your applications. What's the ASCII code? According to that, what's the ASCII code for an uppercase A? Should be column 4, row 1. And what does it say down here?
0041.
Yeah, 0041. B, C. Uppercase A is lowercase a is 61. Okay. So what they've done with Unicode, instead of being 8 digits, this guy right here is actually 16 bits or four digits. So you notice on this one, this is still the standard ASCII code, but look at all the other things that this guy supports. And by the way, this is not all Unicode. This is we could actually do 65,536 different characters, which is basically every character in modern written languages. So now the internet can not only use English, but they can use Japanese. All I got to do is download the codes for what? Yeah, if you ever went to a site and it don't happen much, and you go there and it says you need to download the character set, it pops up there. So what they do is they don't put all these 65,536 codes in the RAM of your machine because they've got to be in there. So they only give you the ones that are used most predominant. But if you go to a site on the internet and you don't support those codes, then it'll ask you if you want to download those sets. If you say no, then you get garbage. You get a bunch of squares up there. If you say yes, you'll get. So if you ever go to a site and you see these white squares up there, it means you don't have the code for that, right? So Unicode, this is what we're using now. But these guys still use the old. These guys still use regular ASCII. But that's only if we need to send text information. That makes sense? Well, it affects that page. Serial communication. Oh, my pictures are not in here. So we can send information two different ways, guys. We can send it serial or we can send it in parallel. The predominant method is serial. What would you think? What would you think the advantage of serial and parallel? It just about always boils down to what? Yeah, cost. So what we do on parallel, we're trying to send all this information and we're trying to send ones and zeros. So what we would do is we would have a separate conductor for each one of these. Normally we have two. Normally each one of them runs their own common. It still looks about the same color. I'll get with you in a minute. Are you leaving? Okay. Some people leave one of my classes. So we run one common. So this would be 1, 2, 3, 4, 5, 6. But so it would require what? 12 conductors. Serial, we would send all our information on one signal wire and then one other conductor. So we'd have two wires. And what I would do is I would come up here and then I would put the bits on here one at a time. So the analogy I use, it's like going to Birmingham on a single lane road. I could get 1 million cars up there, but it would do what? Take forever. Or I could spread that thing out, right? You understand some of the interstates going up to Birmingham turns in like 8 lanes. You get 8 lanes out there, we can send the cars a lot faster, right? You understand that? But that 8-lane interstate costs a heck of a lot more than what? A 2-lane road, right? So the advantage of serial would be that it's a lot cheaper. And this is the predominant method that we communicate with the PLC, and this is the predominant way that we connect PLCs together using some type of serial standard. So RS-232, that's serial. DH-485 is serial, right? You understand? But you got to understand, a lot of times we're communicating with machines, and machines are not fast. So most of the time it would be a waste of time to do what? To use parallel anyway. So Ethernet. Wi-Fi is what? Serial. Right? Your cell phone, and the information they send you on the cell phone is serial, right? Because we only have one air, right? So center communication is slower, but it's a heck of a lot cheaper. Parallel is faster for the same technology, but it would be a heck of a lot more expensive. 1 bit at a time through transmission. Usually we split it up into frames. It starts off with something called a header. And we have a data. And then we have what we call a trailer. In networking, you might hear them called packets. So packets. Those two terms are the same thing. We'll send out a frame. Then the header usually contains all your address and information, and your trailer usually contains your error checking. Baud rate, basically, this is the speed of the serial. And it's usually labeled in kilobits per second. Well, yeah, but it gets a lot faster. That's what you need to look at the interface to see what it is. This is the problem we have with using this guy. The communication on this guy, the fastest this guy supports is 9,600 bits per second. And the problem we have, and we'll show y'all this if I can get it communicating with it, is that we have the ability to monitor the states of the inputs. Now, on this guy, if you flip a switch, you'll have to wait before it shows you it's closed. This guy, I don't know what it is. I think this is 19.2 kilobits per second. So this guy over here is going to be basically instantaneous. And I think the 1000s are too. So we're not going to be using these guys, but they're nice to show and tell. They still work. So baud rate is confusing with actually bit speed. So the baud rate and the bit speed don't have to be the same. The baud rate is currently the signal transitions of a carrier. And then they can let multiple bits ride on the same carrier, which is really, really neat. It uses something called quadrature amplitude modulation, which we're not going to talk about. But what it lets multiple bits ride on the same carrier. So if I could let binary digits. So if I could ride 4 bits, 4 binary digits on each carrier, that would give me 16 combinations. So that'd be 9,600 times 16. That's how fast you would be sending the bits. So baud rate, originally that was the speed, because that's before we could modulate, right? Understand, they figured out how to modulate these things. But now they don't usually give you the baud rate; they give you the bit speed. So when they say you got that's what they give you. They give you the bit speed. Now, when you talk about the bandwidth on your internet service provider, they don't tell you the baud rate of the carrier. They tell you how many bits or how many bits you can put on. If that makes sense. Framing, this is the process of putting the information inside what we call a frame. Networking, we call it a packet. So these are exactly the same thing. And basically what we do, we start off with a header, then the data, then a trailer. And that might be in the text, I'm not sure. So Eric, usually the header is the address and information. It says who this frame is indicated for. Sometimes it tells us the number of how big the data pack, how big the data portion is. And then the trailer is usually something that the receiver can use to decide if the information that it got sent was correct. The trailer. Sort of like a trailer you pull behind a car. This is RS-232. We don't do this anymore. Is this in the textbook about the framing bits included? Probably not. Parity might be on the test. Error. So RS-232, the frame is only, the frame technically was only 9 bits. It's a 9-bit frame. And it could only carry 7 bits of data because the ASCII code is a 7-bit code, right? Huh? Yeah, it's 9, but it all depends. How many they actually use depends on the Originally, when RS-232 came out, it used a 24-pin connector. But you could actually communicate with 2 completely different things. Eventually, they moved over to a 9-pin. So what was happening is if we wasn't sending any data, the output would stay at a solid logic level. And then your receiver would be coming over here. And then what they would do is they would shift it down for one time. And this was what we call the start bit. So it'd be like if you're on a ship, they use a code when they flash stuff at you, right? You understand? So they use the flags. You ever seen them use the flags? Well, what they'll do is before they send any data, they'll cross them like that. And that means I'm fixing to send you data. That would be sort of like the start bit. And then they come up and do what? Then they're going to send so many codes for you. And then they would come up and end it with a single code that comes in and says, okay, if the data I sent you was right or data I sent you was wrong. Originally, they used something called parity. I'm sorry, it was a 10-bit frame, because then we had a stop bit right here. I'm sorry. Now this is okay, but what we're doing now is that on this, when I send information across my network here, it's going to use a frame. But that frame is going to be big. What they've decided is, I'm sending one ASCII character at the same time. Well, that just don't make sense, right? You're trying to download something from the internet and you're doing it 10 bits at a time. So what they did is they spread the frame out. So now a typical frame is like 4,096 bytes, 8-bit information. That's a lot of bytes. And they had to come up with a different method of determining if it was correct or not correct. So this was strictly for what we call the RS-232 standard right here. This is the way we send data in a frame. But we still use parity. So understanding the frame size, basically a frame consists of three parts. It consists of a what? A header, data, and then a trailer. The header, it contains information about what's going on in the frame. So, TCP iframe, that would say, this is what we use to transfer information over the internet. We use something called TCP, transmission TCP, I'm sorry. TCP. And what that does, that identifies the frame. Okay, so we have what we call a TCP frame. Some of y'all might have heard, on the internet we use something called TCP IP. Most of y'all have heard of IP. IP is the way we address things. TCP is how we put the frames together. And the frame is pretty good size. And that header contains a lot of information. It contains who transmitted the data, where it's supposed to go, right? You understand how many bytes or how much information is in the data frame. And then the trailer, what it is, it uses another code called CRC, cycle redundancy, which is another code that indicates that its packet, and that would be the packet for that frame because it's serial, right? You understand? So what we're doing is that, okay, what makes up a packet all depends on what protocol you're using. And what's a protocol? Basically, yeah, it's an agreed upon way of doing something, right? So Ethernet uses TCP, and it distinguishes what's in the header, what's in the data, and what's in the trailer. What type of error correcting it uses. Usually in the memory of the PLC, we still use something called parity, because parity, the memory in your computer is laid out in 8 binary digits. Anybody know what we call 8 binary digits? It's got a name. Yeah, byte. And we're losing that term. Now we use the term gigs, and we use the term, we say I got 8 gigs of memory. It's actually 8 gigabytes is how much you got in your machine. So the memory inside there is documented in 8 binary bits, or 8 binary digits. And we need to get out of the way because I'm throwing that all out anytime. So a single digit in binary, we refer to that as a bit. So a byte would be 8 bits. And that's the way the memory is still laid out in these machines. No matter if you're doing 64 bits or 128 bits or 16, the memory's still laid out in bytes. It's just that if you transfer 16 bits of information, you go out there and grab 2 bytes of memory. So all we're going to do with parity is we add an additional bit. Huh? No, you don't add. Used to, we sacrificed one. So when ASCII came out, it was a 7-bit code. Even though we were sending 8 bits of information, it was a 7-bit code because they sacrificed one of the bits for parity. But we don't do that anymore. So now the memory in your machine or the memory in here is probably set up in 8 bits, and then they add a 9th bit for parity.
So if we don't have no parity, it's sort of like an error message.
You used to get parity errors when your memory, it'd pop up on your memory. That was bad. You don't hardly see it anymore because the memory, that's back in the day when memory was not that reliable. So they wanted to keep a constant check of what information the information that you stored was the information that you read. So originally in your old computers, they use parity. Now they don't usually use parity because the memory is so reliable in our machines now because we've gone through so many generations of these things, right? But if you got into if you got into a machine where the memory has got to be right, like in a file, like in a server or something like that, they use some type of error correcting or checking method. So parity's still out there. So we have two parities we can run. We can have what we call odd parity or even parity. And you can still see that on your serial port. I don't know about this, but we got something on our computer called control panel. And then in system, and device managers. You can get to the device manager several different ways. And if you got any of these COM ports out there, port settings, one of the things I can specify is what? Parity. Right now it's not using parity. So this is the speed. This is bits per second, so that means I'm using, this is set up for 9600 bits per second. It's set up for how many data bits? 8 data bits, right? Okay. And right now it's using what? Yeah, but I've got two options. But actually we got some, but these are the two that we talk about. I can either set it for what? Even, or I can set it for odd. Or I can set it as a mark, which means that when it comes to the parity bit, it always generates a 1. Or I can set it to what they call a space, which means it always generates a 0. Now what determines what you need to use is you need whatever you're communicating with. So this guy right here requires a certain parity. Now luckily what happens is that we used to have to do this. Most now, all our devices are what we call PNP. You know what that stands for? Not a transistor. It stands for plug and play. So usually what happens, you can even see this on a USB stick. You plug it in, if a little thing pops up, says there, I'm installing the driver, and what does the driver do? Well, it comes in here and sets all this stuff up for you automatically. So normally most people don't go in and see this. You don't know it's out there, right? So when I hook up to this PLC, it's going to set the parity for me. Most of these guys use none.
We had that problem a lot of times in the off-brand that used to, I think it was better.
Yeah, some of them's weird. Some of them won't, when it installs the driver, it specifies which port you put in. You ever notice that?
Yeah.
And you plug it in a different slot, it don't work.
Yeah.
And it won't find the driver because it knows it's already got that driver installed. And you have to move it back to the original port and then it works fine. Some of them let you move them around, so y'all remember that. So a mark means when it comes time in the frame, when it comes time for parity, it will always generate a 1. And if you put it on space, when it comes time for the parity bit inside the frame, it will always generate a 0. If you put none, then what you've done is you've reduced your frame size by 1 bit. And of course, it don't seem like much, but when you're doing 9,200 bits per second, right, you understand, you're saving 1 bit per byte. That's a pretty good deal of time.
Is that why, like, with iPhones, you have to do certain things? Like, you can't, versus like an Android. Like an Android, I can plug them into multiple computers. iPhones, you can't do that.
That's what
Well, Apple, you can plug it in there, but what Apple requires
you can't run our program.
Yeah. It requires you to have an application to run. Most Android phones, if you plug it in, you can download the pictures off of it. Yeah. iPhones, you can't download the pictures. The iPhones, you can't download the pictures without running the what? You have the iTunes. So even parity, what we do, it has nothing to do with whether a number is even, and it has nothing to do with a number of odd. What it does is it takes the parity bit and it will put a 1 in the parity bit or a 0 to keep the total number of ones in your data bits always even. That makes sense? So let's just come up with a code. What was our code for an uppercase C?
4-3.
So that's a 7-bit code. So originally ASCII was a 7-bit. Then what I'm going to do is I'm going to come over here and I'm going to add another bit up here at the front, and this is going to be the parity bit. Now, which parity do we want to run? Do y'all want to run even or odd?
Even.
Okay, so let's say I'm going to run even parity. How many ones are in that 7-bit? 3. What do I need to do to make it an even number?
Add another 1.
I'll put a 1 out here in the parity bit. And then what your receiver does is your receiver, all it has to do now is count the number of ones. If it comes up to be even, it drops the parity bit. It don't need it anymore. It's just in there for error checking, right? You understand? And then it says, okay, the data's not okay. The data's okay. If it's not, then what it would do, and I didn't give y'all, there's a bunch of codes in the ASCII code. I gave y'all the front part. Oh, I'm sorry. It's got 2 columns there, right? What's the first 2 columns? It's got like acts. Y'all see acts and NACs and frames in the ASCII code chart. The first two columns. Yeah, the first 2 columns. Column 0 and column 1. What's in there? A bunch of letters, right? Null, start of text, end of text, start of transmission, end of the technician. But let's just look at 2. Y'all see one called NAC, N-A-K? What code is that?
Yeah, negative number.
And then you see act, right? So what would happen is that if the receiver got the wrong parity, it could send back a not acknowledge. It would send back that code for a not acknowledge, and then the transmitter would retransmit the last data. And we call this handshake. So what you're doing is the 2 devices, you send information to the computer, to the receiver, and it lets you know if it's okay or not okay. And the 2 main codes would be acknowledge and not acknowledge. So I would send it data. It says, okay, I'm running even parity. I've got an even number of ones, so it would send back an acknowledge. And then it would send it the next code and the next code and the next code. If it didn't receive the right parity, if it counted them and came up with the wrong thing, right, it would send back a not acknowledge, and the transmitter would retransmit the last data. And that way, it basically would, but we still have problems with this. So if one of these bits, so this is what I'm trying to send. And let's say if one of the bits changed, then this would count and it would come up and get 1, 2, 3, 4, 5, and now it would say, okay, the data's wrong. Because I'm expecting an even number of ones, and I just counted a what? Odd number. Now this is the problem we have with parity. 2-bit changes. Parity would say the data's okay. But what it's been proven is parity is about 95% accurate. So your hard drive on your computer, when you get information off your mass storage devices, how accurate do you want it to be? You don't want it to be 95% accurate. You want it to be 99.9999% accurate. So they use another method that we won't get into. It's called CRC, which is cyclic redundancy check, and that's what we normally use now. It's 99.99999% accurate. So that means we still have a bit change every once in a while, but it's very seldom. This is what the internet uses. It uses CRC. We have two types of devices on a network, and this is important to know. I don't know if this explains it why. So DTEs, these are data terminal equipment. These are the devices that transmit the data or receive the data. So my computer is a DTE, the data terminal equipment. So data terminal equipment, that's the termination or the end of the chain, right? You understand that? That makes sense. Data communication switch equipment is the devices that it flows through to get to the DTE. So if you got a router at your house, it's a DCE. If you got a switch at your house, it's a DCE. If you got a gateway at your house, it's a DCE. If you got a printer on your network, it's a DTE, right? Understand? So data terminal equipment, this is what actually originates the information and receives it. The problem, what's a PLC? DTE. It either transmits information to you or it receives information. Right? So computers will always be DTEs and PLC will be DTE. But if I run it through something to get here, then that would be, so if I'm going from Ethernet over to DH485, then we would have to go through some type of DCE, right? Something that converts it from RS-232. DET, no, computers are the DTEs. Yeah, they're the terminals. They're the terminators. That's terminators where it ends at, right? Does that make sense? And this depends on the way you make your cables. If you look at this Ethernet cable and you just flipped it over and looked at the color code, it goes orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. If you look at the other end, it's going to be green, white, green. Because we had to do what? Because they're connecting to two DTEs. So two DTEs. No, Ethernet is the way we connect things. The cable is not considered to be a DTE. It's the media of what it flows through. DTEs and DCEs are actually going to be devices that the information flows through, right? A modem is a DCE. That's exactly right. So most of y'all have modems. If you got internet at your house, you probably got a modem, right? And that's a DC. But whatever computer you're getting to would be a DTE, right? Everybody okay?
So a cell phone,
That's fact. The cell tower, no, what'd you say? The cell phone would be a DTE. The cell tower would be a what? DCE. Because it's going through there. That's not where it's going. Eventually it ends up to someplace, right? Goes through a lot of stuff before it gets. Responds to messages transmitted by DTEs. So this is not your wiring. This is the devices that it flows to. Networking, we call them nodes, by the way. Anything that connects to a network, device that connects to the network, they call it nodes. NOD. So usually on some of your PLC networks, you set up one PLC as being what we call the master. It usually holds all the tables and everything that you use inside your PLC, and then all your other PLCs would be what we call slaves. And it's usually something that you have to configure. We try to do some networking with PLCs in the PLC3 class. We've only taught it once. And we didn't get to it at that time, unfortunately. But the course is still being set up. That's when we take a manufacturing system and convert it from a Allen Bradley PLC over to Siemens. Pretty neat class. I don't know if y'all will be able to take that or not. 'Cause y'all don't know what y'all take, right? I need to find that list.
Y'all converted. Y'all converted those?
No, we go, no, we don't. We take it back to Allen Bradley when we get through. So that's what we do in our class. We go back to Allen. So y'all don't know what class, y'all don't know from semester to semester what y'all gonna take.
I have the list that
Okay.
you got.
I'm missing one like this, so.
So a multi-master network would just mean you have more than one PLC that's designated as a master. Does that make sense? Usually, on a master slave, anything your other PLCs need to access that's not put in their memory, it would access it from the master.
You have an advanced
I sure can.
programmable, an advanced programmable,
Controller,
yeah.
that's still around Allen Bradley.
Okay.
So this is not quite what we would look at, because a DCE would never be the end, right? You understand that? So what we would have is we'd have to have something over. We would have to have another what? DTE somewhere. So simplex is one direction, right? You understand that? We do this sometimes. If I don't need information back, then it would be simplex. And the perfect example of simplex is your radio in your car. One direction, right? From the what? Transmitter to receiver. Full duplex usually requires more conductors because, and we're not talking about the path. You understand, if I've got a signal wire, I've got to have at least one what? Common. So here they're showing like it's one wire, right? Are we okay? Oh, sorry. I thought we'd already gone through simplex, duplex, and full duplex. Yeah, but this drawing in your book is not exactly right. There will be no DCEs by itself. Yeah, somewhere out here we got to have a DTE out here. I don't know what page this is on your book. So a DCE will never be out there by itself, right? What page?
Page 30.
So DCEs is what it travels through to get between DTEs. And it depends on what we're going to connect our cable through. So we have what we call straight through cables. These are designed to connect DTEs to DCEs. And then we have what we call crossover cables that are designed to connect DTEs to DTEs. Because if you didn't, they would be transmitting on the same wire, right? That sounds like. The problem is I don't know it, guys. I don't know.
Oh.
We'll get you one made out of rubber.
Right.
Well, I'll be able to anyway. I need to get me a different thing. So if you flip this over right here and you look at the color code, it goes orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. If you flip this over and look at this, now this is the same way. So this is a straight through cable. This wouldn't work. don't have any crossover cables. These are straight through cables. So I wouldn't be able to hook this into this PLC because I need what we call a crossover cable. And I've got quite a few over there. Simplex is what?
Is transmit
One direction. Half duplex,
Both directions, one at a time.
one at a time. Full duplex.
Simultaneous.
So these are three types of modules. You still might run into these. These are called handheld programmers. I don't think I don't know where it's at. I need to find it. I just picked up this course, by the way. This was originally Miss Wilson's course, and then Mr. Perry. I don't know if y'all knew Mr. Perry. Now he passed away. So you won't see many of these anymore. We still have them in robotics. In robotics, we call these teach pendants. Yeah, still using these handheld programmers on there.
All the robots down there. This is very simple, but not the same.
Well, it's got the commands on it. So this would have, and I don't know if I can make this bigger, guys. I'll try. I don't know if we can make it big enough so y'all can actually see some of the keys. But this has keys on it that specifically allows us to program what's required by the PLC. So there's that is an output core. Okay. This is the symbol of a contact. This is a symbol for what we call a latching, unlatching. So this is a symbol for a down drop with and we'll see these when I program these in there. So I don't know if I've got RS Logic still running. Yes, it is. So that would be these would be on the key. So what I would do if I wanted to put a coil in here, a simulated coil, I would drag that down, right? You understand? But on a handheld programmer, you would hit a button. Okay. And then of course on those, if I wanted to put a down drop like this, then I can come up and do something like this. Okay. So what's happening is but instead of having the symbols up here, they would actually be where? On a key on the pendant. And what we would do, instead of me having to drag down the symbols, I would hit this and it would be inserted into the phone. Right now it says I got an E as an error, so I know something's wrong with this rung. Of course because I hadn't assigned anything. And here I can come up here and I can insert another rung. I'll try to, oops. So I've added another rung, right? Well, what we would do on that handheld programmer is we'd have a watt on there. We'd have a key that allowed me to do this. Of course, this rung's definitely got a problem because it's going between L1 and L2. That's short circuit, right? So you won't be able to clear that. So what this is asking for, it's asking for me. See the question mark up there? So it's asking for something. I'm not giving it what it needs. And we'll show you that. But on a handheld programmer, all that would be there. So see, there's your, so up here, latch and unlatch. We'll talk about all these. There they are right there. Can't put it in that last set. So on this one, a computer, we have the symbols and we just drag them into where we want to put them, right? On a handheld programmer, we would have what? We would actually have the symbols on the program. And also on a dedicated programmer, a dedicated terminal. Originally, like I was telling you, you still might run into some of these. The industry, for some reason, don't like to replace things that's working. So that means if you get into an old plant like US Steel that's been around, they're fixing to open back up, you're going to run into really old stuff and you're going to run into really new stuff, right? You understand? So the art furnish they're putting on there is going to have really new stuff. It's going to have a lot of PLCs and all this other kind of stuff. You get into some of these older lines over there, you're going to run into a lot of relays and stuff like that. You might run into a PLC that has a dedicated terminal that you got to haul out there and plug into that. You can't use your laptop. And that's what the next picture is. So the next picture is showing us basically a dedicated terminal. Now the problem with these little old pendants is that you're limited to what you can see. Usually you only can see one rung at a time. So that's all the display shows you is one rung at a time. And if you've got 50 rungs, you would have to go through it, and you could not basically visualize. If you can't visualize what the previous rung is, you got problems, right? You know what I'm saying? So what they went to next is they went to dedicated terminals, which means your PLC still has a lot of processing power in it. It's got the operating system and handles all the communications, but what it makes the display a lot bigger. And usually you go from a keyboard over to a touchscreen. And that's the next thing that the PowerPoint shows you. Which should be this guy right here. But notice it's still got basically the same thing. So you still program it, but now your symbols are still over here on your keypad. Now the predominant way of programming now is with what? Laptop. What advantage does a laptop have? Well, it has a bunch, right? You understand? And so normally we have to go between what interface the PLC uses, and we have to have some type of converter that goes between there. What's nice about Ethernet is you don't have to have a converter, because just about all your laptops now, if you buy one, by the way, you need to buy. Laptops are getting thinner and thinner and thinner and thinner, right? You understand that? So every time we get ones, we make sure we get one with an Ethernet jack on.
Chromebooks don't have it.
Yeah, but odds are you can get a dongle. A dongle is that we call them dongles, where you can plug it in. I guarantee you can buy one where you can plug it into a USB port and you can get an Ethernet jack out of it. I'd almost guarantee it. It would really surprise me. We can still get floppy drives. We've got one. We still got some stuff we have that's on floppy disks. And so we've got a floppy disk that runs off USB, right? You understand that? So you can get
Really? I've
yeah.
got some old files.
And you can buy those floppy, you can buy the drive, the little drives, they plug right in the USB slot. Work fine. Yeah. But now, instead of having the dedicated keys, we have to run an application, right? You understand? And of course, the application we're going to look at is RS Logic 500 in this class. And I'll try to show y'all the new version, RS Logic 5000. But what you're going to find out, guys, once you learn how to program in ladder language, you can move to just about any PLC. It's just about, say, because ladder language is about the same. It's an international language. And it's still the predominant language of programming PLCs. And that's what we teach. And you'd have to go to some type of engineering school or something to get your other languages that's available. So this is what we use there. This is it. Being unauthorized personnel, you can password protect the CPU in these things. So please don't do that. Right? So it's just like anybody password protect your phone. If you don't, now they got them with facial recognition, right? So now you don't even have the touch thing on it like the fingerprint scanner. But a lot of them gives you, originally the iPhone was you could set it up for what we call a PIN so you can let other people unlock it. Now it's up to 6 digits. Yeah, they still have PIN, but you have to tell it which way you want to do it. So mine pops up every once in a while, like when you get out of the shower and you hit it and it pop up and once you've entered it. You should.
Never. Ever since I've had cell phone.
Every one of them gives you the ability to password protect.
I know, but I've never.
Either password, most of them are going to some type of biometrics, like a fingerprint scanner, what with now. But a lot of your new phones that they have facial recognition available. You look at it, huh?
Yeah, I scan it.
I figured if this one had it, now it ends up in Russia somewhere.
Well, the problem is if they don't know it, they can't get to your information. They can wipe it. They could take it in and wipe it, but even the technicians can't get into it.
Kind of like ransom.
So it's, if you don't have a password on your phone, you got a bunch of stuff in there, then you need to protect it.
That's the key. I never put anything in there that you do that.
Well, I've got so many passwords that different companies have different requirements on passwords. You know. And plus, I don't use my same password here that I use at home. And then you go to, most people pay that most of their bills on phone now are on. All my computers are password protected. Common communication settings off. Most of your PLCs are only off when you unplug them. Then we can put the PLC into what we call offline mode. I hadn't seen disable and then run mode. And what's the run mode? So offline, if you got your computer offline, your PLC offline, it means it's just not running a program. And then online means or if it's run, if you're in the run mode, then it's going to actually run the program, your program that's in there. So I guess where's my camera at? So most of these, we have access to 2 of them on the 5000 or the 500 series, and this is still pretty standard. So here's the CPU. Of course, it's got a switch on it. You see the 3 positions we can put the switch, if it focuses in. I can put it in run, I can put it remote, or I can put it in program. Okay? Now remote allows you to switch it from your computer. Of course, mine's not connected to anything. So right here, so right now I've got it set for what? Offline. And then I can either download means to send it to it, and then upload means that bring it down, and then we can switch it to run here. We can't see it because I don't have a PLC hooked up.
You mean offline?
Offline means we're offline, so this is on RS Logic 500, you cannot modify a program when you're online with the PLC. So if you're going to modify a program, you have to take your computer offline, right? You understand that? And then you can modify the program. RS Logic 5000 allows you to modify a program in the run mode.
Is it a one-way communication?
What you mean?
Those have duplex machines?
What?
The PLC.
The PLC can or can't be. It depends on what you're communicating with and what's available to you. Most of them are full duplex because you can send information to the PLC and get stuff back to your computer at the same time.
I can see what you're on 5.
Huh?
I can see what on 5. That'd be an advantage. Trainer keep things open.
Well, what 5000 does is 5000 keeps a copy of the original run, so you can modify it. You can try it out. If it don't work, you can always go back to where you're at. You don't have to document that. What we do here, every time we change a program and we try to download it again, it'll ask us, if you want to need it, if you're going to save the different version, then you have to save it yourself. Our thumb drive is. class gets out at 12:10, right? Are you okay? Anybody need a break? Was that, okay, I'll take a 2-minute break. We'll come back and finish this chapter up. About every hour, guys. You see, about every hour, y'all, somebody needs to do what? Because Rich will go straight through.
What's that guy's name I was talking to? Remember him?
That guy's name you were talking to. Oh, that's Trey.
I've had classes with him. It was over 2 years ago. I'll get it. It's embarrassing not to remember.
It takes me a while to learn names.
You got a million kids, or adults. You got a bunch of these. I wouldn't say it was Anthony's. It was not. No. I'll go ask you. You realize I'm nearly 72 years old.
I'm 68.
But you're a lot younger than me.
How much?
You ain't got rubber bands or nothing. Did you have a zip tie on that?
No. Yeah.
So for the first, electrical, we, that, those slides are on our blackboard, right?
Supposed to be.
Terrence got
I'm gonna check and make sure. So here they are. So they're in course content under lecture slides. An introduction to electricity.
That thing you were showing stuff there, we're gonna be able to use that,
What's that?
that program, that ladder logic, where you drag it on.
Now, this is what we're learning.
We're gonna be able to use it. Okay, I was thinking you were gonna be drawing.
No.
Like it is before. Ladder. So actually, if I'm not a mistake, it's showing error right off.
If you got it, if you don't have it in the right syntax.
When's our first test going?
Monday.
So we're gonna take the, what's it like, pre-test? Don't we have to take like a pre-test before first test? What do they call that?
We have what we call a post-test.
Post-test, okay.
You get to look at that.
For the first test? That's a quiz. Yeah.
Are you playing?
Sometimes you get. Yeah, well, we can take the time for you.
Oh, y'all love these telescopes. Y'all got that down? So guys, this is what we have to go through. First of all, one of the first things we do is we need to establish communication with the PLC. And what's the driver? In computers, what's the driver?
It's
The interface. Storage, right?
So all the computer can do is run programs. Everything you see the computer does, every piece of equipment is run by a program. A program that is written to control a specific piece of equipment is referred to as a driver. So an operating system is just thousands of drivers. And then normally on an operating system, you have a program that allows you to control those drivers or control the operating system, and it's referred to as the shell. Shell. S-H-E-L. So this is the shell used by Windows. It's called Explorer. Now what can I do with Explorer? I can open files, I can do this, I can do that. So normally if you install a new piece of equipment, especially USB, and it's not, and the driver is not already in there, what's nice about USB, it allows the driver to be in the device itself. So when you plug it in, it says, I'm here. Windows says, well, who are you? And it says, well, I'm here. And it says, well, I don't have a driver. And it says, okay, here's the driver, and it installs there. And then once it's installed, it goes through the same thing. It says, okay, who's there? It says, I'm here.
And it says, okay, I've already got a driver for you, right? You understand? So a driver is a special piece of equipment. It's a program that's written specifically to run a special piece of equipment or some type of peripheral. So now you know what it's doing when you plug that USB stick and that little thing pops up there and says, I'm installing the what? Driver. So we've got all different types of communication that we can hook up with this PLC right now. So before I can communicate with this thing, I got to make sure I have what installed? Driver. So to install the driver for your PLC, Alan Bradley uses something called RS Links, and this comes with the package that you install. And this is even on RS Logic 5000, which is the new version. So the first thing you're going to have to do is establish a connection to the PLC. So RS Links, and then here it is, and it comes up here and says communication, and it says what? Configure driver. So this is where I have the ability to come in here, and here's all the available drivers, depending on how I'm all going to connect to the PLC. I'm connecting through DH, this guy right here. So I install that thing, and then when I installed it, one of the first things it wanted to know was what? Which COM port I'm using. COM is the serial port. Are we okay? Makes sense? We're okay. So one thing you have to do is figure out, unfortunately, did I just delete that? Yeah. So unfortunately, so I'm going to hit this, right? And I'm going to hit add. And then I'm going to say okay. And the first thing it wants to know is what COM port. So what do I need to know? What COM port? I need to know a COM port that's free, right? You know, how do we find that out?
By looking at anything plugged into it.
Well, the problem is all we got is USB ports, and it's been assigned. These guys, PNP means they assign it. So I'm going to go to my computer, go to properties, go to device manager. This is what's nice about Ethernet. You don't have to go through this. And so here's the COM ports right there. So I'm using COM3. I've already stuck it in there once, so we're okay. A while ago it wasn't there, so it added it. Okay. So I'm going to use COM3. Where am I at? Okay. It says it's running. We can click on it. We can stop it if we want to. Okay. And then what we can do, then we can go back here and look at the links and see who's out there. And there it is, and there's my PLC. This is MicroLogic 1100, and right now I don't have a name. We'll show you later on how you can actually give the PLC a name. Okay. So I've established a communication with it. So this now I've loaded in the programming application, RS Logic 500. And then I'm going to go up here to comms, and I'm going to say who's active. So you could actually have this thing on a network hooked up to multiple PLCs. And here's a PLC right there, right? Y'all see that? I'm going to click on OK. And it's got a program in there. So we'll see. We'll see what's up. So this is the actual program that. So what we did is we just uploaded whatever was in the PLC. But I don't want to do that. I'm going to come up here and start a new program, new, which is what y'all do. And we're not going to save this. And first thing it's going to ask me to do is what? Select what type of PLC, the CPU on this thing. This information, there's a white label on the side of this PLC, and it's a MicroLogic 1100 version B. I'm gonna come up here and find the MicroLogic 1100 version B. Okay, now I'm ready. And we want to create a program. So what we have is we have a bunch of input modules. And this is a fixed PLC. So the first module number on this is a fixed PLC. The CPU does not take up a module number. So my first module number available is module 0. Y'all follow me so far? So I'm gonna pull down a contact. Y'all know what a contact is?
Yeah.
Okay. What is it? Well, it's just a contact. Well, it's the actual physical thing that makes the circuit. Yeah. So a light switch has contacts on it. And when you flip the switch up, those contacts are open. When you switch it up, the lights are supposed to come on, by the way, if it's up. So up's supposed to be on and down's supposed to be off unless it's a 2-way or 3-way switch. Huh? Yeah, I know. What they did that is they figured out that most of the time when you accidentally hit a switch, you knock it down. So that's why they wanted up to be on. So if you accidentally hit it, it would not turn it on. It would do what? Turn it off, or it wouldn't turn it on accidentally. So this is representing a contact. Wait a second. This is the last rung in the program. And on Allen Bradley, the last rung is always the end rung. You cannot put anything on the end rung. So the first thing I'm going to have to do is put a rung where I can put a program into. Here's my little rung guy, right? I'm going to drag it down. I see that green arrow. That means that's okay to place it there, Rich, and I replaced the rung. The first rung number that Allen Bradley signs is 0. So all the rungs has different numbers, right? Makes sense. Now I can come up here and I can pull down this. I can pull down this. Oops. Now notice when I get it down here, any place that turns green, I can put it there. So I'm going to put it right there. And then I'm going to bring down an output. This is actually going to be generate an output. Okay. Then this is a down drop. Just moved it there. That's not good. Let's see. I'll pull this guy here out. There we go. And then I'm going to put another contact right here. And it says I still have an error. Now what I've got to do is I've got to assign these to the inputs coming into the PLC. Now on Allen Bradley, the way we start this is we have to assign it an address. So up here on the question, I'm going to say I, which stands for what? Input. Right? And then we come up here and I'm going to put a colon. And then I'm going to put a module number or a slot number. On these, we start with 0. Okay. And then I'm going to say, okay, that's module 0. Which terminal do you want to use? We're going to use terminal 0. Make sense? Okay. Now, this on the camera. But what I've just done is I've assigned this to this switch right here, 0. Okay? Does that make sense? Okay. Then I'm going to come over here, and I can't use the same one, so I'm going to put input, and then I'm going to put colon 0/1, so that's going to be the next switch down. I've addressed that. Are we okay? Then what I'm going to do is this is going to be one of the outputs, so I'm going to turn on a light up here. I'm going to come up here in outputs, I'm going to put O for output. And then I'm going to put a colon, then module 0, and I'm going to use output 0. Are we okay? That makes sense. Now this is a symbol for a coil. A coil has contacts. So we have what we call internal contacts. These are in software. So what I'm going to do is I'm going to come over here on this one, and I'm going to say I'm going to assign this to output 0/0. So what means if I energize this, that's what we say when we put power across a coil, even though this is not a real coil, it's a simulated coil in a program. What it does is coils control contacts. And notice I gave this contact the same number or same address as that contact. So that means anytime I energize this guy, this contact over here is going to close also. Okay, I'm going to come up here. It still says I have an error, and on Allen Bradley, it don't clear up. So this little guy up here that's got this check mark up here, what I need to do is verify the file. Oh, I didn't put my slash in there. So it says I still got an error, and then what happens is a little box down there, and it says I need to specify this to the bit level. And it says it's in rung 1. I'm sorry, it's in rung 0, right? Line 1. So it's instruction 1. So it's that one right there. So what didn't I put right there? I didn't put a slash. And notice the actual input number dropped down. Okay, so see the error. So if you come up here and you hit that check, now the rung is okay.
What is VUL, man? VUL.
This is the bulletin number. All this is the type of module. This is a part number that Allen Bradley throws up. These are the only PLCs. I mean, Allen Bradley RS Logic's the only one to do that. That's a good point.
Let's just say I wanted to connect another contact coming from that output. Would it be
Doing
like,
what?
Huh?
Doing what?
Like right over on the, let's say if it was two contacts on the same.
Well, odds are we wouldn't put 2 contacts from the same device on the same rung.
But I'm saying maybe you could have.
Well, we could come down here and I can come down here and insert another rung. Okay. And then I can come up here and add another contact. But what I'm going to do with this contact is I'm going to assign it to this same output. Output colon. No, I want it to be controlled by the same coil. Relays can have multiple contacts. Now on a mechanical relay, I think I passed that around the other day, right? On a mechanical relay, you're going to be limited to the number of contacts you can control. On computers, basically the number of contacts can be almost infinite. We'll just run out of address, and we'll show you all the problem we have as we go across. So if I put output 0/1, I would have to have another output coil somewhere, right? Understand what I'm saying?
Yeah, that's what I was.
First, if I try to check it, it still says I have an error, and it says I have a missing output. So every rung's got to have a load, right? Understand? So we'll come down here and we'll assign it to another output, which is going to turn on light. And we'll talk about this in a minute. We're going to require y'all to get used to doing some stuff here. So this is my program. I'll come up here. I'm going to check it to make sure it's okay. And notice I have right now I can program it because my computer's offline. Okay. So what we're going to do is we're going to come up here and we're going to do what? I'm going to download it into the PLC. It said, okay, we're going to save this. This is where you can give this a title. Oops. Of course, it could have been that big. And this right here is where you would tell it where you wanted to put it at. So I'm going to come up here and I'm going to put it on my desktop so I can keep up with these. Okay. Okay, then it says the file is already exists, replace it. So I've got it out there. So it says my PLC is and then it says right now we need to switch it from what? In run mode, so we need to switch it to the program mode. Now on this guy, you would switch it. You could put it in remote, and what's nice about remote is you can switch it between modes with your computer. If you want to use this switch, what's nice about this is you can come up here and you can put it in the run mode and then you can take the switch out. And that means what? Nobody can change your program without the what? Without the key. If you put it into remote mode, then anybody that logs into this thing is going to be able to change it. Normally fixed PLCs, you don't have that capabilities. Processors in remote mode, we switch it to it's developing the image, it's compiling it over. Then I'm going to switch back to the run mode. You want to go online. Now, online means I'm actually going to be able to monitor what's going on in the program. So right now it shows me, here's my power rails, and they both come green. See that? What I'm going to do is I'm going to come up to switch 0, which is going to be our stop button. And I'm going to turn it on all the time. So it's turned on all the time. This is simulating what we call a stop button. And notice it went green, which means now it is true. Okay, and what's it waiting on? Input 1. It can't get anything from this, so this is an output. So this is a standard circuit you run into. Anytime you run into a control and it's got a start-stop button on it, this is the way this works. So this would be the stop button. This would be the start button. What I'm going to do with this button is I'm going to just momentarily switch it. And notice it went true for a heartbeat, then it went false. But what I did is I created a secondary path now where we can seal this thing in. So this would be what you out there. If you're out in the industry and you got a stop button and a start button, this is the circuit right here. You hit the start button, you let it go. And it's a momentary contact button, so it's only made when you do what? When you press it. But it seals itself in, right? You understand? So this is a seal-in circuit. Some people call it a memory circuit. Some people call it a 3-wire circuit because there's 3 wire numbers between here and there. And of course, you can probably see, I'm not on the camera, you can see the 2 outputs turned on. Can you see the lights over there? Stop button, so here's my stop. And both lights should have gone off on the front of the PLC. Can y'all see it? Nothing's happening until I do what? It's a start, but this is momentary. Oops. Momentary is the other one. And that's our first PLC program. Now, if I needed to run a motor, what I would do is I would hook the motor up to the output. Not the motor. I would hook a relay up to the output, and then the output would bring in the what? The output would bring in the relay, and the relay would run the motor. Very seldom do we hook up motors directly to the PLC. We hook up a bunch of lights, because lights don't require a lot of current, right? You understand? And that's our first program. Is that hard? 2 runs in this thing. So if I was doing this in relays, I would have to have a relay. I'd have 2 relays at least. Still going to have the push buttons, right? You understand? We're simulating the push buttons with these switches up here. And you can see this guy here works the same way. So what we're doing, but that don't have to be a switch. It could be the input from a sensor that indicates something's in the right position. Right? You understand that?
You said that's like for contact for.
Yeah, this is we assigned it to an external port, right? You understand? So I said assign it to input 0. So that switch is actually hooked up to this first input right here.
Is it only hot and you push the button and hold it down, or is it?
I don't know what you mean by hot. We're not dealing with hots or colds. We're dealing with ones and zeros.
It's charged.
No, we're dealing with ones and zeros. So it's true when it's
It
close.
locks in. What do you call it?
This is a simulated contact. This is totally in the program, right? You understand? But when this guy right here energizes, when we simulate power across it, what it does, it generates a true output over here. Now these outputs are what you're going to be using right here, right? You understand? So what we'll do is we'll take up all our input devices and hook it up to the input ports, and then we'll take our output devices and hook it here. Switches are going to give us either a 1 or a 0. but it's going to do it with a voltage level
Put it off in the program.
without hooking the switch.
Like bypass.
Yeah, this is what we call forcing, and you got to be really, really careful. So when I come over here to the inputs, so here's the inputs, and notice there's nothing in here but ones and zeros. So I'm gonna come over here and just close another switch, and you see as I close the switches, sorry, then it's associated. All I get is a what? 1. See that? Although that's no, we're talking about right here. The switches are right. So this is switch 0. Now this is switch 1. This is hooked up to port 2. This is hooked up to port 3. This is hooked up to port 4. Can you see them? Port 5. So this is what they call an image table. I can come up here and double click on this sucker right here, and I can change it to a 1. Oh, not there. Drop that on my phone. So we'll show you how to do it next class. This is called forcing, and you got to be extremely careful when you force these PLCs to assume something is a 1 or assume something is a 0. Because if you turn on an output and there's somebody out there, so what you just did is you defeated every safety feature that's been built into your PLC program that prevents people from getting crushed and run over and crushed. And you can go back and, so what you need to do when you force these things, you need to make sure you know exactly what you're doing. We had a guy at US Steel killed. I think, did I tell you the story? Somebody went and did what? They forced a contact that wasn't locked out. They locked out the other one, but they didn't think about locking out everything where the person was within. They locked out one thing that they were working on, and the guy went in there and forced the relay. And a door came up and pinched the guy in two. I almost called an accident out of US Steel. The strips on number 4 galvanized line would run about 700 feet a minute. You know, they had a clamp that would come down when it welded the strips together. And I was in there forcing a relay, and I was bringing down that side clamp. Luckily, the strip they were running that day was too small, and the side clamp was missing. But if it would have come down and clamped down on that line running 750 feet a minute, it would have caused some damage. So I lucked out that time. Like, you know you're doing this. And the problem is on those, the relay houses, you couldn't see the line from where the relay houses was. So you had to be in communication with somebody that was out there. Okay, guys, see y'all Wednesday. By the way, we're going into chapter 3 on Wednesday. What's chapter 3? Numbering systems and codes. We already looked at one code, though, ASCII. And that's what our first lab is going to be due. So our first lab, our first lab is a homework lab, and it's done in the lab book. So you're going to have what? Your lab book. It's going to be due Monday. What's that? Do I have what on Blackboard? You're not going to do lab 1 until we go over it. We're going to go over what's in lab 1 on Wednesday. Does that make sense now? If you don't have your lab book, I think I can run that one off for you, but that's it, guys. You know, I can do a little bit for you, but I can't copy the whole book, right?
You can walk on water to show us where the rock is.